Hi, in this video we're going to be discussing about Kirchhoff's laws, what they are and where they are used. But before delving down into this video, I'm going to request you guys to watch my previous video that is on the fundamental definitions of circuit analysis, the terminologies of circuit analysis, that is the branch, the node and loop. So that knowledge is going to be tested again and again in the upcoming videos and in the questions that you'll have on your tests, assignments, or the examinations as well. So before going any further, just pause this video and go back to the previous one on circuit analysis. A link is going to be posted in the description as well as in the end screen as well. I'm going to tag that video in the end screen as well, end screen to this video actually. So stay tuned till the end of this video, but for the time being, for the moment, go back to the previous video and watch that. Moving on, Kirchhoff's laws. Once you have watched the previous video and you have some fundamental knowledge about branches, nodes, and loops, so given the previous definitions, we are now in a position to consider Kirchhoff's laws named after the German scientist Gustav Robert Kirchhoff. That is the name of the scientist. I know it's heavy, but German names are usually like this. So, yeah, Gustav Robert Kirchhoff. The first law that we have at hand is the Kirchhoff's current law, or the KCL. It states that the algebraic sum of the currents entering any node is zero. Suppose we have a complex circuit and we have several different nodes in that circuit. The current on node 1, say for instance on node 1, all the currents entering from all the branches entering that node are going to be equal to the current on all the branches that are leaving that node. An arrowhead will be given to you pointing away from the node or towards the node so that you may guess the direction of the current flowing in or out of the circuit, out of that node particularly. And then you'll have a dot representing that node. But even if you don't have the arrowheads or the dot, you may easily test your knowledge. You may easily apply that concept of nodes and branches to firstly identify the node in the circuit, and then you may just guess the direction of the current and see whether your calculations yield a positive sign. If it is a positive sign, then it means your assumption about the direction of the current in the first place, the first assumption that you made was correct. And then if your answer, your calculation yields a negative value, that means that your assumption was incorrect in the first place and the direction of the current is actually reverse of what you had assumed in the beginning. The second law that we have is the Kirchhoff's voltage law, which states that the algebraic sum of the voltages around any loop is zero. I'm not going to go into any details as for now because we need to solve problems in order to see how Kirchhoff's laws work. But here's the statement once more: the algebraic sum of the voltages around any loop is zero. Suppose if we have a complex circuit again, and that circuit has many different loops, several different loops, the sum of the voltages around any loop is going to be equal to zero. This is what Kirchhoff's voltage law states. We're going to visualize these things ahead in the videos, so stay tuned. The significance of Kirchhoff's laws. Well, why do we need these laws? For example, we have that Ohm's law with us. V is equal to IR, which is the fundamental circuit analysis technique. It's circuit analysis law that we apply in order to analyze a circuit, in order to find out the resistance. If we are given with a voltage or a current, we can easily identify a resistance, calculate a resistance to be precise. And then if we have the voltage and the resistance value given to us, we may easily deduce the value of the current. So why on earth do we need to use Kirchhoff's laws? Well, in the first place, Kirchhoff's laws are used wherever there are more than one resistors or elements in a circuit. Suppose we have two resistors in series, we still can combine those two resistors and make use of Ohm's law effectively. But suppose that we have more resistors and more elements connected in series or in parallel, how are we used to how can we just do away with that thing, that complexity in the circuit? And still, suppose that we somehow use effectively Ohm's law and calculate the respective values that are to be calculated in that circuit. What if transistors or inductors or capacitors are given to us? How are we going to analyze that circuit? So this is where Kirchhoff's laws come in handy to us. And again, just to reiterate, these laws require the definition of branch, node, and loop. So go back to the previous video while pausing this video, or move on ahead in order to watch that video, the link to that video in the end. Assuming that we have this circuit and we have to apply KCL on each node, and we have to write the equation of the Kirchhoff's current law on each node of the circuit. First of all, we need to identify the total number of nodes that we have, and this has been given to us in the circuit. So I'm going to be using this color. The first node that I have is this, and this is given to me in the circuit. The second node is this. The third one is, I don't know, yeah, the third one is this, and this is the fourth one, while this is the fifth one. I have all the nodes stated, and now I need to just label these nodes and make compartments for them. For node 1, what is the equation going to be? If you notice, if first of all, I need an assumption to apply KCL. I'm going to say that the current that is entering a node is going to be negative, right? And the current that is leaving a node is going to be positive. Now this is my assumption. You guys may go otherwise. You guys may consider a current entering a node as positive and a current leaving the node as negative. It's totally up to you. For node 1, I1 is the current entering the node. I1 is going to be the current that is entering. So it's going like this. So the equation is going to be minus I1, because I have assumed that a current that is entering a node is going to be negative. So here it is. And then we have the sum, a current that is leaving the node, that is I2. It is going to be I2. And then we have a current that is leaving again, and that is I3, and all of this is eventually going to sum to 0. So this is a simple equation of KCL, Kirchhoff's law, the current law basically, and here it is. That's all. That's all that you have to do to apply KCL at a given node in a given circuit. Next, I have node 2. So I'm going to first label and make a compartment for node 2, and then I'm going to write the equation for node 2. For node 2, there are 3 branches associated with node 2, and a current that leaves the circuit, the node number 2 is I6, and another one is I1, and I5 is going to enter. So writing I5 in the beginning, and then we have I6, and then we have I1. And all of this is going to sum to 0. That's all. Now, similarly, node 3, node 3 is here, and there are 4 branches associated with node 3. So basically we have I5 as the one leaving. So I'm going to write I5, and then we have I4 entering, so that is going to be negative. And then I have I2 entering, that is going to be negative again. And then I have I7 as leaving, so that is going to be positive. All of this is going to sum up to 0. Simple. Now I have, if I could just write the equation for node 4, it's going to be simple. Again, node 4, I'm going to first make a compartment for node 4, and I'm going to write the equation. The equation is for node 4, I3 is the one entering, so that's going to be negative. And then I have I4 as the one leaving, so that is going to be positive. I4, and then let's do it again. This does not sound good. I4, and then we have I8 as the one leaving, so that is going to be positive. All of this is eventually going to sum to 0. Next in line, we have the last node of this circuit, that is node 5. And for node 5, we have a simple equation. There are going to be 3 branches associated to node 5, and I6, if you could see, I6 is the one entering node 5. That is going to be negative. And then we have I7 as entering, so that is going to be, well, entering, so that's going to be a negative. Sorry, that is going to be negative. And afterwards we have I8 as entering, so that's going to be negative. All of this is going to sum to 0. So this was basically it from the Kirchoff's current law, and here we have the 5 different equations of all the nodes in the given circuit, and we had to write the KCL equations for each node. Here it is. Suppose that we have another circuit with us, and in this circuit this time we're going to be dealing with the Kirchhoff's voltage law, or KVL simply. Suppose we have a 30-volt independent source attached to the circuit, and then we have a 5 volts independent source, and then we have a 15 volts independent source attached to it. What we have to do in order to calculate the voltages in this circuit, or again the currents through this circuit, what we have to do is to find out an assumption that we require. We can assume either that the current is in the clockwise direction, and we can take this as positive, or we may assume that the current is moving in the anti-clockwise direction or the counterclockwise direction, and that is going to be positive. These are both the assumptions, either of which we could make in order to solve our circuit. I'm going to assume for this video that the current is moving in a clockwise direction. So I'm going to make a loop out of this circuit like this, and I'm going to say that it is current I, because only one value of current, only one current is going to be flowing in this loop. This is the loop, and no component or element is attached in parallel to any of the branch. So of course the current is not being divided by any component or branch. Now the first thing that I need to see is whether the current enters the negative terminal of the battery or the independent voltage source, or the positive terminal. If the current enters through the negative and leaves through the positive terminal of the independent voltage source, I'm going to assume its value as negative. So for this purpose, we have minus 15 volts, and then the current enters this resistor. I'm going to sum it up, and then I'm going to write, what am I going to write? Yup, the voltage as it occurs in R3, the resistance number 3. And then I'm going to see whether the current enters the negative terminal or the positive terminal in this source, and this source, the current is again entering through the negative terminal and flows out of the source through the positive terminal. So I'm going to put it minus 30. Next, I'm going to see whether the current enters. No, I'm not going to see the polarity because the resistor is not carrying any sort of polarity. So I'm going to make it positive, sum it up, and then I'm going to write the voltage that appears in R1, which is the first resistance in our circuit, or the first resistor, and then I'm going to see whether the current enters the negative or the positive terminal of the 5 volts battery. So it again enters the negative terminal and leaves to the positive terminal, so again 5 volts, and then I'm going to sum it up, the last one. This is not 20, this is actually, sorry, this is not 3, this is actually 2, because this is the first resistor, this is going to be the second one, and this is going to be the third one. So that was just a flaw in the question. Now I'm going to see in what resistance, through what resistance the current passes, and this is R2, the resistance R2. So I'm going to put it up as V, that is the voltage drop across this resistance R2, and I'm going to equate it to 0. This is it. This is how you apply Kirchhoff's voltage law. So first I'm going to talk about the resistors. Resistors don't carry any polarities with them. So let's talk about a couple of more things regarding resistors. First of all, resistors don't have any polarities, and all of this that is written over here as in VR1, it just tells you that you have a voltage, the voltage drop across R1. So R1 is actually the subscript to V, and then here we're going to be showing it as the voltage drop across R2, and finally we have the voltage drop across R3. We already know using Ohm's law that when two resistors are connected in series with each other, there is a voltage drop. The voltage does not remain same, whereas in parallel connections, the voltage remains same. So this is a series circuit. This all of these resistors, I'm not going to say that they are connected in series because they're not connected to each other at all. But I'm going to say that whenever there is voltage, suppose that this node here carries a voltage of 30 volts, that it does in actual practice, because if here's a ground attached that has 0 volts, and then we have a 30 volt source attached to it, so 30 minus 1 is going to give you the voltage drop, 30 minus 0, sorry, 30 minus 0 is going to give you the voltage drop in this branch. So at this particular point there ought to be a voltage decrement or a voltage decrease. The voltage is not going to remain 30 volts. Had the voltage remained at 30 volts, the current should not have moved, but the current is constantly moving. We already know. Now this is going into the next video, but I'm going to be highlighting this fact as well, and I'm going to be talking more and more about it. The current moves from a potential of higher magnitude, a higher potential, to a potential of lower value, lower magnitude. This is how the current flows. For example, if we have this and we have the ground attached to it, a ground has 0 volts potential, and suppose we have a plus 5 volts potential on the upper side. So what is the potential drop? The potential drop is going to be 5 minus 0. This is how a current I is going to move downwards from 5 volts, positive 5 volts, to 0 volts. And suppose if we have another circuit, we have this as the circuit. This is, let's not call it ground. We have minus 5 volts, and then we have the ground over here, that is 0 volts. So current I is going to move downwards again from 0 to minus 5 volts. Uh, that is from a higher potential to a lower potential. So I'm going to be talking more about this in the upcoming videos. Let's not worry about these things. The thing that you should be worried about right now is KVL, and this video was dedicated towards Kirchoff's laws. So here it is. This is Rafi Khan from Team Persiscon, signing off.